Welcome to N is for Networking. I'm Holly Metlitsky, bringing you a fresh perspective as someone newer to the industry. Alongside me is Ethan Banks, a seasoned network engineer who enjoys diving into the nitty-gritty of networking concepts. Together, we're here to explore the complexities of networking while keeping things clear and approachable. Today, we're diving into a listener question submitted through our Slack channel. Kieren asked, curious if maybe a topic worth exploring would be the difference between MLAG, lag, stacking, MC-lag. Why are they different but all sound so similar? This is a fantastic question and one that I've asked myself a bunch of times. So these terms seem like networking jargon overload, but we're here to decompose them. We'll unpack each concept and explain how they differ. Whether you're a seasoned professional or someone just stepping into the world of networking, there's something here for you. So let's start with LAG, Link Aggregation Protocol. So my understanding of this in layman's terms is where you take multiple links and configure them as one single logical link. How accurate is this understanding, Ethan?
Yeah, you got it. That is it in a nutshell. You're taking multiple links and you're configuring them as one single logical link so that once you've got them all configured and they're acting as a bundle, now you can configure them as an interface and do things to them like you would any other physical switch port, only now you're working with this logical link aggregation bundle.
So leads me to my next question. Why? Why do we want to aggregate links?
So there's a bunch of reasons, right? There's a bunch of reasons. One, it came up in episode 9 when you and I were chatting about this, and that is redundancy. It's nice to have more than one link. So a really a common scheme might be between two switches. You've got, you need to uplink between them for whatever reason. So rather than having one physical wire, you can have two physical wire and two interfaces. But you don't want to deal with them as two separate interfaces. You just maybe you want to deal with them as one. So you bundle them together as a link aggregation bundle. And so you can work on them as if it's one link, but it's actually two. So if the cable fails or the interface has got a problem or something like that, you've got some redundancy. The two switches, the uplink is still good, even though one of the links failed. So that's one reason. Another reason here is spanning tree. So you can, without link aggregation, plug in two parallel links. And let's just imagine in our minds two switches, Holly, switch A and switch B, and we run a single cable between them. There's no loop there, right? Because we just got the one cable between them. But as soon as we put a second cable in parallel in between switch A and switch B, now we've created a loop because switch A can talk to switch B, which can go right back around and talk to switch A again over that other cable. And Ethernet doesn't deal with loops. And to prevent loops, we've got the spanning tree protocol. Spanning tree protocol communicates between switches so that they understand how they're all interconnected and will put a looping link into a blocking state so that there is so that's physically connected, but you're actually not using it. It's in a blocking state so that you're not forwarding any traffic across it, meaning that link is wasted. And when you're designing solutions for your customers, Holly, do they really love a lot of wasted links?
Oh, of course, all the time. It's what I do best. No, I mean, anything wasted is money badly spent. So everything comes back to cost.
Exactly right. Especially when we're getting into these really much more expensive 100 gig and 200 gig and 400 and 800 and so on. You don't want to have links that are burnt, that are just wasted because of Ethernet not being tolerant of loops. And so having to have spanning tree in there to prevent the loops. It's like, well, I spent how much on those interfaces and that thing's sitting there in a blocking state? No. Yeah. So LACP, or I'm sorry, we haven't even talked about LACP yet. Strike that from the record, listener. I didn't even say that yet. We're just talking about link aggregation. So yeah, one of the ways to get around that problem is to do this link bundling with link aggregation. So,
which I guess, following on from what the listeners haven't heard yet, how do we do this? How do we do it? LAG?
So to form a link aggregation bundle, we need a control protocol. That is, we need a way for the two switches to talk to each other and say, hey, we're going to form a bundle. Okay, yeah. This port is a member of the bundle, and this port's a member of the bundle, and so on. And there's other characteristics that they can share between them to determine that these switch interfaces are a member of a link aggregation bundle, and that is Link Aggregation Control Protocol, LACP. And if you're digging around and you do a search on LACP out there on the internet, you're going to find a couple of standards referenced. Back in the day, it was 802.3 AD, but then it was in 2008 moved to 802.1 AX, the same standard covering the same thing, but it's still really common. You'll see out there 802.3 AD. And then mentioned, people in the know will get snooty and pedantic about it. Well, it's 802.1 AX. Well, yes, it is. It's because decisions were made that in the gigantic body of standards that makes up Ethernet, 802.3 AD, LACP was in the wrong place. And so they moved it to 802.1 AX. Now, by the way, those standards, 802.3 AD and then now 802.1 AX, that's not just LACP. LACP is one part of the larger link aggregation standard, but that's where you'd find that information. And if you see it in vendor documentation or people's blogs talking about 802.1 AX and LACP, it's not the same thing, but LACP is part of all the data that you will find in 802.1 AX. So that's the how. Your LACP as a control protocol is supported on your switch or your servers. By the way, servers can speak LACP. That's a thing. And that is how the link aggregation is going to be formed between the two switches. They're going to use LACP to do that, to have that communication.
All right. So LAG is the link aggregation group, the actual aggregation of the links, and LACP is the protocol defining that. So this now leads me to my own confusion, because at Juniper we call it something, at other vendors I think it's called something else. Maybe you can speak to this a little bit more, because obviously I know at Juniper we call it a link aggregation group, and I think I've been using that quite a lot here. So
yes. So Cisco would call it a port channel on like their Nexus product line that running on XOS. They tend to call it a port channel. Cisco also calls it an ether channel on iOS. You'll see that pretty commonly. As you said, Cisco or Juniper says link aggregation group. Arista says port channel. Aruba says link aggregation group. And I didn't dig any deeper than that. They're all talking about the same thing. It's how do we bundle a group of physical ports into a logical port and treat them and then bundle them together like that. That's it. So there's no marketing. Yeah. I don't know. Whatever. You got to call it something.
And I think going back to our listener's question, Kieren, I think a lot of the confusion comes from, when I was trying to research all these topics, every vendor calls it something different, and you start to think, well, is it the same thing or is it just a different term? And there's no, I don't enjoy using this term, but like a single source of truth for this is what it is, because everybody calls it something different. So it creates a little bit of confusion. So I guess now looking at LAG, can we can do this on switches, servers, hypervisors.
Yep.
I guess going back to what we discussed previously on episode 9, you mentioned hashing. Can you explain this a little bit more? And, why don't we do the round robin forwarding?
Okay, so backing up a step, there's a big question here. When a switch gets a piece of data, a frame, it's got to forward across a member of the link aggregation bundle. How does it decide which member of the link aggregation bundle it's going to forward that frame across? And the answer is it does math, but again, your question is, why don't we just send it out frame by frame, round robin, so that we get this perfectly even distribution across all members of the link aggregation bundle? We talked about this in episode 9 a bit, but the answer is out of order packets. Out of order packets are bad. If packet 3 arrives before packet 2 at a receiver, the receiver is going to be confused, and maybe it can cope with that situation and maybe it can't. At the end of the day, it's a bad thing. We don't want that. And so the switch has to make a decision, an intelligent decision then, to avoid this out of order packet problem. Every flow, a conversation between two hosts, needs to go across the same link aggregation bundle member. So if we got, 4 members in the bundle, we have a flow that comes up. We want the switch to know that every single packet that's a member of this flow is going to go across member 2, let's say, whatever it is. Well, how does it do that? Well, it performs a hashing algorithm. That is, it's going to do math. It's going to look at a bunch of characteristics of the frame and or the packet that it's faced with forwarding, do some math against it, and that math is going to result in an Ether channel member that it's going to send that traffic across. Now, if you think about this, the challenge here, Holly, is that we could end up with some pretty uneven load distribution across the members of the link aggregation bundle. Because you could have a situation like a backup is happening across that link aggregation group. Well, backups are like, they call them an elephant flow, big noisy flow, big fat flow that takes a long time, because backups are like many gigabytes or terabytes of data that's going across the line. And you got all of that data hammering this one line, and the other lines are less used because of hashing. Well, we did the hashing. It's all got to go across member 2. And so that's the challenge here. And so if you start digging into hashing, you want to configure the switch to use a hashing algorithm that is well matched to the kind of traffic that flows through the link aggregation bundle, so that you get a roughly even distribution of packets across the wire. I really wish we could do round robin, honestly. I got to say, I wish that was a possibility. Now that I say that, back in the day, Brocade, when they were still a thing, they're no longer an ongoing concern. They got acquired by Extreme Networks some years back, and their product line went wherever it went. I know a lot of it still exists in the Extreme portfolio. But anyway, they had some kind of a scheme that did like a round robin. I digress. We don't
it existed, but it's gone now.
It existed at some point. It existed because I remember a bunch of us sitting in a room talking to Brocade going, wait, you do, and they were like, yeah, we support it because a customer asked for it, but we don't recommend it. It's kind of like, we do it, but don't do this kind of thing is kind of how I remember that conversation. Anyway, hashing. So the key here, Holly, is we want to do hashing on characteristics of the frames and or packets, so that we get a pretty good distribution of traffic across all the members of the link aggregation bundle. So way back in the day, when switches were simple, we could do source and destination MAC addresses. How do you think that one did?
Well, not too great. I don't think we do it now anyways. It's a bit too basic. I'm not quite sure how you, if it's a really long packet, how you splitting that up or frame.
It's too basic. And if you're going between, the problem with source and destination MAC addresses especially is that a lot of hosts might be hiding behind a same MAC address. If there's a gateway on your local network from traffic that's coming from a different network segment, everything's going to look like it's coming from the router, even though it could be a bunch of different hosts, even though it looks like it's coming from the router. And so you don't have a lot of unique MAC addresses that are seen necessarily. All that to say, source and destination MACs, too simple. We could ramp it up and do a little bit better. Source and destination IP addresses, where you get more variety. Not so much hiding behind a MAC address, even better than that, and something much more common, source and destination IP addresses paired with source and destination port numbers for the conversation. Now, that's what I was saying, a flow earlier. In my head, that's a flow. A source and destination IP address paired with a specific port number and source port number and destination port number. Like You're hitting a web server on port 443. And so you can hash on your IP address, the server's IP address, your source port number that was used to initiate that conversation on TCP, and TCP port 443. Your source port destination is going to be really unique because it's randomized. Every time you send out a conversation, you initiate a conversation to some host out there. It's this random thing between 0 and 65, 535. So you get a lot of entropy there. You get a lot of variety in the number of port numbers. So when you're hashing on that, then you get a better spread. You're going to end up with better math that results in a better spread across the Ethernet link aggregation bundle members. All right, shutting up for a second. How am I doing?
got a question. So again, I'm not quite sure if this is just Juniper specific, as I mean, I've only configured devices with Juniper, but I know that you can choose to either do per flow or per packet. Now, I guess why, I know per flow is usually recommended. Why and what's the difference between the two?
So per packet would be going back to that round robin thing that I'm talking about. Now, if it is what I think it is, I have not configured, back in my days of doing Juniper admin work, that was never an option. So it could be that Juniper's ramped this up to the point where they're, like I was talking about that Brocade solution that we were talking about way back in the day. It's like, we offer it, but don't do it, kind of thing. Maybe Juniper's happy with this because per packet, what that sounds like to me would be perfectly even load distribution across those links, 100%. That's how without actually digging into the documentation, looking at that means to me, it's not hashing, it's round robin most likely, or some other kind of very even load distribution scheme. Round robin's not the only thing in the world, but they could be doing other sorts of queue management, but I'm speculating without digging into the resources. But yeah, it sounds like you've got that option. And I'll further speculate, having not researched it, that this will be tied to the Ethernet chipset that they've baked onto that switch, that certain switch ASICs are going to be better able to cope with a per packet or round robin style load balancing across a link aggregation group than other ones. But that's me guessing. That's me making educated guesses.
Yeah, I think by default we do per flow. So I guess per flow is more session based. Like you said, you open the session and that flow is going, where per packet is literally like keeping that packet together and sending it. And then the next packet comes and you send that one and so forth. So. Unless things have changed radically in the Ethernet chipset world since I was paying that close attention, I don't think per packet's going to be universally available. I think it's going to be selected on particular switch models would support and other ones would not. Very possible.
Yeah. Okay. So we talked about, that was all link aggregation and what's actually going on under the hood on some level. We talked about LACP as the control protocol that helps you establish the link aggregation bundle. We talked a bit about hashing. You can get crazy with certain switches on how you do the hashing. We mentioned all the way up through source destination and source destination IPs and port numbers. That's pretty common. But you can get even more granular than that. I was looking at some Arista documentation where you can basically pick your field. I want you to hash on whatever the field is, and they give you all kinds of different choices in there. But again, I think that's going to depend on the switch ASIC, and what's actually under the hood, what's going to be available to you. More modern chips, you're going to have more flexibility. Older chips and some network gear lasts a very long time. And you can definitely run into stuff that's 10 plus years old sitting in a closet somewhere, aren't going to be able to do fancy hashing, let's say, where you can arbitrarily assign the field you want the hashing to happen on. All of that conversation, Holly, that was a setup to start talking about MLAG and MCLAG. So why don't you set this part of the conversation up for us?
Yes, I would love to, because I spent quite some time digging into a hole of trying to differentiate between MLAG and MCLAG, of which it started off with, okay, MLAG, multi-chassis link aggregation, and MCLAG, I found something that said multi-cluster. And I thought, okay, those must be different. And then upon further reading, it started to converge and they seem to be the same thing. And depending on what source I found, it called it something different and mostly described it as the same thing. So I couldn't quite understand, am I really bad at researching? Or perhaps these two things actually are the same thing. Again, I'm really glad Kieren brought this up because trying to decipher this on your own by like a quick Google search, you can get 101 different answers from different vendors, different sources, all telling you contradictory things. So please tell me, MLAG and MCLAG, are they the same thing? I hope so, because that would make my life quite simple. They're
the same thing. Yeah, they're the same
Great.
thing. So MLAG, MCLAG, they're two acronyms that mean the same thing. Generally speaking, multi-chassis link aggregation. This is where you're taking two physical switches and pairing them together so that you can distribute a link aggregation group across them. That's it. That's it in a nutshell. So you can have switch 1 and switch 2. And you can have, let's say switch 1 and switch 2 are members of an MLAG team, if you will. And you can have a third switch 3, that is connecting to them. And as you're configuring an ether channel or a port channel or a link aggregation group, depending on which vendor you're talking about, on switch 3, 2 of the links go to switch 1 and 2 of the other links go to switch 2. But to switch 3, it looks like one thing, one link aggregation bundle, even though it's physically been split between switch 1 and switch 2. And that's it. That's MLAG, that's MCLAG, that's other acronyms depending on who you're talking to. You had mentioned multi-cluster lag. I hadn't run into that one. I don't know what that exactly is, but
I think it's still the same thing. Probably just a bad source. Black hole. I found every source out there, and I was like, you know what? Our podcast is here to clarify these things because if I'm confused, probably a lot of people new to the industry are also confused. So I thought I'll save my confusion here and perhaps you can help me clear that up. There's a problem. There is a problem that has resulted in this. There is no industry standard for this technology, for taking two physical switches and making them act as the same logical switch for purposes of link aggregation. Everybody does it their own way. It's proprietary. There's no standard that you're going to and saying, oh, okay, if you want to do this whole MLAG thing, MLAG is, an IETF RFC or it's a 802.3 something. No, there isn't anything like that. And that's why there's the confusion, because every vendor comes up with their own way to do it, to do the same thing. So what's happening under the hood and how it's getting done is unique. And they brand it uniquely. So I talk to a lot of vendors in my job. That's part of what I do, right? And vendors have a tough job of differentiating one from another. That's one of the things they want to do. And how do they do it? It's like, it's the same thing. Vendor A and vendor B have a technology that does the same thing, but they want to differentiate from one another. So how do they differentiate? Sometimes the best they can do is branding. They just rename it or relabel it or come up with a unique acronym so that it sounds different or fancier or special in some way, even though practically speaking, there may be some implementation differences that have some merit to them that are worth considering. But by and large, it's the same thing. It does the same thing. In MLAG, MCLAG, it's the same thing. There's no distinction there. Other than perhaps some brander. Yeah, pick what you like. And it's up to you as the engineer, honestly, if you're out there listening, it's up to you to be able to dig in under the hood and go, okay, what is this actually accomplishing for me? Because you have a business obligation to meet. You've got something you're doing network design for. And just because the vendor calls it something different or calls it something fancy, forget what it's called. What does it do? And if it does the same thing, it does the same thing. And so you can understand, therefore, if the business need is being met that you are that you're trying to meet with your network design solution. So, Okay, for the purpose of this episode, let's stick with MLAG.
Okay.
We'll go with that. Cool. So now that we know that MLAG and MCLAG and all the rest are the same, how do we actually implement this? I know we obviously connecting links, but we know what link aggregation is using LACP. So how do we do it here?
The trick is that the two switches need to share control information. They need to know about each other and know that, hey, we're part of a team. We're part of a peer group that are going to be behaving as a single logical switch to talk to other hosts that want to make link aggregation bundles with us. And so for any kind of an MLAG implementation that you see, you're going to find that there's a peer link that is dedicated to those two switches talking to one another. That peer link is sharing all that control information so that the two switches know what the other one is doing. Oh, we're about to form a bundle, and there's 2 ports on your switch that are part of the bundle, and there's 2 ports on my switch that are part of the bundle. Cool. And they can keep track of all that information across that peer link. And again, that's a dedicated port, a pair of ports between the 2 switches that are going to carry that information. And you might have a backup peer link port because the peer link is super important. If the peer link falls over, fails in some way between the 2 switches that are a member of the MLAG group, then you got problems. You got issues where the 2 switches can't talk to each other anymore. And so you might have a backup peer link option as well. So 2 switches with a peer link and possibly a backup peer link between the 2 of them. So they're sharing information. You're going to configure them with whatever the specific commands are, and that varies widely by vendor. And one of the switches is probably going to be the primary, like, hey, somebody's got to be in charge, and it's me. I'm the primary. Okay, you're the primary. And then the secondary will follow the primary's lead. There also tends to be requirements for things like identical VLANs. You need to have, if you look at switch 1 that's a member of this MLAG group and look at the VLAN database, it should be the same on switch 2. They should both have all the same VLANs. And there may be some other characteristics and requirements as well of being identical so that the switches are able to handle any sort of traffic that comes at them in the same way. If you didn't have the same VLANs, say VLAN 3 was on one of the switches but not on the other, but the way the hashing worked out, the VLAN 3 frame went to a switch that didn't have VLAN 3 configured on it. Now what happens? That sort of a thing would be problematic. So
yeah, in terms of that, you're saying the switches need to be the same, but is it possible for those links that are creating that peer link and in the MLAG formation, you know what type of traffic is coming through those links? So can you have other links on the switch that perhaps are different? So if you know that, I don't know, VLAN 20 is only going to go through switch A via port 1, and on B, it's not going to have that traffic. Is that okay because it's not going through the link aggregation, or do they really have to have the same information?
They really got to have the same information. Now, that doesn't mean every port is identically configured on each switch, but things like your VLANs, your VLAN database are almost assuredly going to be the same, because in the situation of a inter-switch link where you're connecting one switch to a pair of switches that are acting as an MLAG group, you're almost always going to be using those as a VLAN trunk or tagged ports. And so you can't predict which side of the MLAG group that a frame might go up. And so you got to be able to handle whatever that VLAN is that's sent up, no matter which side it ends up getting hashed to. And there's this other concerns too about things like, well, what about the spanning tree topology? So if you've got differences in the VLAN database, your spanning tree topology is different because spanning trees tend to run per VLAN. And so, again, it would depend on the role that the MLAG group is playing. But generally speaking, I mean, I know for sure that on some of these MLAGs I've configured in the past, if you have a difference in the VLAN database, it's going to flag it and go, I'm sorry, I can't bring the MLAG group up because we have a VLAN database mismatch between these two switches. You have to rectify this before we can join. It's not going to allow it. There's topology challenges there, and I understand exactly what you're saying, Holly, because I can see that. It's like, well, if I know for sure that this VLAN's only ever going to need to show up on this switch and not the other one, wouldn't that be okay? Because effectively we're making both switches act as part of the same layer 2 domain. No, it's really not okay. Again, making a lot of assumptions on how you're going to use that MLAG group, but the vendors are not going to allow you to do that, because that'd be a pretty hefty foot gun. You could really shoot yourself there, and that could be bad. So that's a pretty common requirement. There may be other identical sort of requirements as well. So we got switches. The switches tend to be identical switches, the same model, the same operating system, and all that stuff. Not always. It depends a lot on your vendor and what they allow and what they don't allow. But that tends to be a common implementation where you've got two identical switches running the same operating system exactly. They've got the peer link and maybe a backup peer link between them. They've been configured as a group. And now you can configure your multi-chassis link aggregation group across them, if you will. You got that. You got your identical VLAN requirement, and then we're going to be using as a control protocol almost always LACP is our control protocol, 802.1 AX as of 2008 anyway. And it works the same as it did with two switches talking to each other, or server to switch, just works like it always did. Only the bundle is now split across two different switches on one end. So has that come together in your head, kind of how that's working?
Yeah, it has. I think which we'll get to later, we do things a little bit differently, and it's not really something I have worked on. But there is a problem that I have heard of that I guess I just haven't really dived into it for reasons I don't deal with it often enough to dive into it. But I've heard of this situation where it's called like a split brain when you're dealing with MLAG. Could you speak to that a little bit? Because I've heard of it, but I'm not quite sure what it means.
Yeah, the split brain problem is when the peer link is severed between the two members of the MLAG group. And so rather the peer link, the point of it is, again, it's that control channel between the two members of the MLAG group. That is how the two of them communicate with each other and stay in touch. It's how they keep things like your spanning tree topology straight, and who the members of the link bundle are, and how to do your forwarding across those link bundles, and so on. If that link is broken, the peer link is broken, remember how I said typically in an MLAG bundle, you've got someone's your primary and someone's your secondary. Well, now if they can't see each other, they can both think they're primary. Split brain. They both are now think they're the one. They're the primary, which goes back to why you might want to have a backup peer link, just in case. Yeah. This is a bad problem because now you've got two people in charge, and two people in charge is never a good thing. They're doing their own calculations on things like spanning tree and how to do forwarding, and they may assume the other one is gone and make their calculations on the assumptions that, the team member, the group member I was working with is gone now. I'm the one left. I will do all the things myself and begin doing forwarding in a way that leads to a topology loop. So you could have basically an Ethernet loop where traffic begins to loop out, and that's going to take your network down in a hurry, almost always. And other just unpredictable weirdness. Your link bundles might fall over. Other strange behavior can happen when split brain is ongoing. So that's a potential concern. It's a rare problem, but it's the kind of thing that you want to be aware of. Could be a concern, and how you're going to handle that. And So because the vendor implementations of MLAG vary from vendor to vendor, how they go, this isn't going to be consistent for everybody, but there may be behaviors you can configure, like what do I do if the two of us lose touch with each other? And and maybe the answer is we're going to shut down supports to avoid topology loop, that kind of a challenge. But that's what split brain is all about. And it's something you want to design. You want to make sure that doesn't happen is the big idea.
All right. So I think anything else that needs to be configured or considered when we're setting up MLAG?
Well, one other point I guess that's worth mentioning is because of the fact that there's two different switches, and if you're like rebooting the network, you're bringing up different things.
Yes.
If a switch knows it's part of an MLAG bundle, it may, as it's coming up, sit and wait and listen to the network for a while before it starts forwarding, because it wants to know before it begins forwarding, is everybody here? Are we all together? Are all our links up? Is everything cool? Is the topology stable? Nothing's changing, right? And then we'll start forwarding, but it'll keep things in a blocking state before it actually sends traffic out the door. So this could be a couple of minutes. This could be a few minutes, depending on how. Again, every vendor does this their own way. So it could be again a few minutes before things are forwarding. So it could be you're like, this switch is up. Why am I not getting traffic? And you're like freaking out. Well, right. It could be this is an intentional delay put in part by the vendor. It's going to be something you can configure, but just to make sure that the network is stable and cool and good to go. It's like, all right, everything's good. I'm happy. Let's forward. Let's go.
Yeah.
But any network engineer who's in a situation of like upgrading an operating system or needed to reboot a switch because reasons, and then you're waiting for traffic to begin forwarding, and you're waiting and you're waiting and you're like, oh my gosh, what's happening right now? And you're like freaking out because traffic is not moving across the network. It could be something like this is happening because of the nature of the MLAG bundle and how it behaves on boot up. That's an unusual thing, but yeah, there you go. It's worth mentioning.
Would it be recommended to boot the primary switch first in the bundle? Or
talk to your vendor as far as that goes. The way I've always handled those situations is, who do I want to end up as the primary when this is said and done? And that'll be the first one that I cycle. So I would do like if one is the primary and two is the secondary. Let me think about this. So I would upgrade the NOS on the primary. It would fail over to the secondary. That would become the primary. Switch 2 would become the primary. Then I would upgrade switch 2. Primary would fail back to switch 1, and then switch 2 would come back up and rejoin as the secondary is how that would end up. So there's a little thinking you got to do, mental gymnastics to decide what order you want to do it in. But there are, for a lot of things like this, you can set a flag or set a variable of some kind that says, okay, I want this switch to always be the primary or the master or whatever the terminology is that the vendor uses. And so you can so you can say, as soon as both are on, if you detect that, if you can see each other, but you detect that the switch 2 is the primary. No, I want switch 1 to always be the primary. And you got a flag set, and then you can, the role will automatically swap once the topology is stable again. But again, very dependent on vendor and what they offer and how fussy you want to get with the configuration.
Yeah, I feel good. I feel good about MLAG or MCLAG.
Okay.
Got some clarity there. It's quite nice. I think I knew what it was and I knew what it did, but I guess I just didn't have a solid name for it. So you're
ready to blow it all up now and talk about virtual chassis?
I was going to say I'm ready to say, well, I actually don't use this. So yes, exactly that.
So you don't use this because you typically are selling virtual chassis?
Yes.
Okay.
And I think only sometimes certain devices support MCLAG. I'm not quite sure, but it's really not something that we do on the regular. Kind of, if a customer really wants to do it, we can figure it out. But we very much lead with virtual chassis. Which in that, we talk about MLAG and we talk about how those switches have to be the same. Now, when we talk about virtual chassis, I guess for people who don't know, a virtual chassis is when you link two switches together through a VC port, a virtual chassis port, they on the switch itself, and they act as one big switch. So I guess in comparison to MLAG, you've got two switches which are almost kind of duplicated. They know the same things. They're acting as copies to some extent, where virtual chassis, they almost think they are one. Is that correct?
Yeah, I think that's the big difference there, and that's a good way to think about it. With MLAG, all you're unifying, the only control plane element that you're unifying is just making link aggregation bundles. With a virtual chassis, you're taking a bunch of physical switches, interconnecting them with, in Juniper's case, virtual chassis ports, and they look like and behave like one big switch. You use one management IP to log into them. You see other members of that virtual chassis like a line card in a chassis. It can be, in fact, in Juniper's world, I believe you can have a line card mode. That is, you can put a switch in line card mode, if you will, and there's a couple other modes too. I forget what Juniper calls them all, but that's your job, Holly. You're supposed to know that. It's the Juniper person here. But right, rather than MLAG, where it's just the link aggregation bundle control information that's shared between two devices, a virtual chassis is two or more. There's some kind of a limit to it, but you can connect several different switches together and have them act like one gigantic switch. And the virtual chassis ports are used for control information in between the devices to keep the configurations all synchronized and programmed as needs be, and so on. But they act like one big monster switch. It's kind of like a chassis switch, this is where the virtual chassis comes from. I mean, a physical chassis switch, you've got a chassis with a backplane in it, and you can take line cards, slide them in, and they become part of that chassis switch. That chassis switch is also going to have some kind of an engine card, or Cisco would call it a supervisor card. Juniper calls them routing engines, I believe. Tell me if I'm wrong.
Well, we don't do chassis switches, so I only know about virtual chassis.
Wow. You've had chassis routers. I mean, I used to run MX chassis, back in the day.
We had routers,
but not chassis switches. Okay, fair enough. Yeah, I used to run Juniper MX chassis. The MX routers, love the things dearly. Yeah. I could make those things do anything. They were incredible boxes. Anyway, the virtual chassis is that concept of a physical chassis where you've got a routing engine that does control and so on, a switching engine, a supervisor engine in Cisco parlance, and then a series of line cards that are all part of it, interconnected with a backplane inside of that chassis. Virtual chassis is kind of that, but connected over the network, interconnected with your virtual chassis ports. That's how I like to think of them. And I know in Juniper's world, because I was reading on this before we recorded, you've got flexibility there. Not every device has to be the exact same switch model. You can mix and match a bunch of different Juniper switch models to make up the virtual chassis. And you say you lead with that. How do you actually sell that? Do you sell like a couple of bigger boxes that are like the brains of the virtual chassis and smaller switches that are more like line cards, or how do you configure it?
Not necessarily. I think it's really customer dependent. It really depends on what you need. Because, in a virtual chassis, if you need certain ports that a bigger box can provide, but you don't need all of those, then you can mix and match to what you need, I guess. So it's really use case dependent. It's not necessarily, I would recommend you start with the bigger boxes this and build with smaller boxes, or vice versa. It's just, what are your requirements, and we'll figure out what you need from there.
Yeah, I was impressed with how flexible it was because early days, I remember when the Juniper Virtual Chassis solution was announced, I think it was fairly regimented. You could do as many as 4 boxes, and they had to be specific models and specific Junos version and so on. And, having caught up with it, many years on, it's like, okay, this is flexible. You can do all kinds of things with it. But the big difference here, we're kind of wandering away into the weeds, Holly. But I mean, I think the big difference here to understand between virtual chassis and MLAG is virtual chassis gives you one point of management, one IP address that handles the management of all of these physical switches as if it's one big monster switch.
Yeah.
So that's the big idea there. And again, there's no industry standard for this. You're not going to be mixing and matching vendors in a virtual chassis. It's all going to be a Juniper solution or a Cisco solution. I don't even know if Cisco has a virtual chassis solution as such. Boy, it's been a while since I've looked. Not that I can think of, but that doesn't mean much. Arista just announced their SWAG technology, switch port aggregation group, which they're calling a stacking technology, but it looks to me more like a virtual chassis. I got to read up on it a little bit more because they literally just announced this as they're recording it like this week.
I mean, that leads me to my next question would be, I know Kieren mentioned stacking, not actually virtual chassis, but speaking from my experience, what is the difference between stacking and virtual chassis?
Stacking is a lot like virtual chassis, but it's more the physical form of it. The way it takes is more specific. So a stackable switch is usually got a proprietary stack port of some kind in the back, and you're usually you're stacking these in a closet because maybe it's grow as you go as you grow, or grow as you go. There we go. You start small and you need to add more ports as time goes on. And so you want to add another switch to the stack rather than saying, well, eventually I'm going to need 250 ports in this closet. You can just start with 96, a couple of 48 port switches, and then add to the stack as you grow. So you don't have to spend all that money on a great big switch at once. You can spread that spend out over a few different years. That's really the guts of why stacking came about as a technology, in my mind anyway. A chassis switch would have been another way to go. You put a chassis switch in the closet, add a line card as you go and need more ports. And I've seen both. I've seen both approaches taken by companies as they go. Chassis tend to be a big investment and they eat up a lot of real estate in the rack. But anyway, so stacking and stackable switches, you've got a physical switch with a stacking port in the back. You have to add pretty much an identical stacking switch to that stack. Doesn't have to have the same port density. Like I used to build way back in the day some Cisco stackables, and you could mix and match. Like they had some 48 port models and some 24 port models and some PoE models and some non-PoE models that were all, if I remember right, could participate in the same stack. They had the same stacking cable in the back, and the stacking cable was often something weird, some unique kind of a terminator, and you would make the stackable in what would end up being a ring topology. So let's say we had 4 switches in the stack. You'd have a cable that went from switch 1 to switch 2, another cable switch 2 to switch 3, another cable switch 3 to switch 4, and then a final cable that would be switch 4 all the way back up to switch 1, which if you do that in your mind, it's like that's a ring. That's what you end up with. Yeah. So that if any one of the stack cables fails, you've still got a unified stack, was the idea behind that, the way you do those stacking. I remember way back, there was a stackable solution that used card edge connectors. So there was this little card with a bunch of pins in it that you'd sit in the bottom of the switch on top, and then we connect to the top of the switch on the bottom. It was a weird thing. I only ever saw that once. That didn't last. Cables tend to be the way.
Yeah.
Yeah.
Also,
it was an odd one.
Pushing that into a rack, I don't quite know how. Got to align them first, put them in together.
I think that's why it didn't last, because it was terrible. Unless you were stacking them on a desk or something, it was like working without
picking up all 4 switches and.
Oh yeah. No, that was terrible. From a management perspective, a stack of switches is like a virtual chassis. You've got
Mm-hmm.
one IP address. There's going to be some member of the stack that is the primary, that is in control of what's going on, and other switches can take over that primary role if that primary switch were to fail. Stackables can have challenges with upgrades where they can be very fussy about the version, the network operating system version that all of them have to run to be able to work together. So you could run into a situation where, hey, I'm going to upgrade stack member 1 to the latest version of the operating system. And you do that, and then it can't rejoin the stack because the other ones are on a different version. And they're like, oh, version incompatibility. Sorry, guys, we can't make you part of the stack. Which, if the whole reason you did stackables was so that you could do an upgrade of one switch at a time and the other ones would carry on and you'd minimize disruption to your business, you might have to upgrade the whole stack at once, all depending. And I would hope that's kind of an old problem. I would hope that as long as you've been keeping up with your iOS, if in the Cisco World version or your Junos versions, you said you don't sell stackables. Juniper doesn't even have a stackable solution. Stackable switches, right?
I don't think so. I'm actually not 100% sure. We might.
It's something I've not looked for one for so long because I worked with stackables for a long time and just never loved that solution.
Also, if we have a virtual chassis, I don't know why you'd want to stack them instead.
Oh, that's it. It's like if I have a virtual chassis, why would I want a stackable? It just doesn't feel like the thing to me.
So I can't confirm. We might. For our listeners, we might, but nothing that I've worked with yet. So
anyway, stackables, a lot like virtual chassis, but a lot more specific and more caveats with the physical form factor, how the stackables are interconnected. There's a bunch of different stacking cable types. Some of them look like just plain old Ethernet cables. Some of them are some wild proprietary things, all depending on who's making it and what the strategy was. And then there can be some management caveats with stackables, and where they can be, again, fussy about every member of the stack having a certain version of the operating system for them to all work together, or get fussy. It's like, oh, you have a different version, we're not going to allow you to join the stack, and so on, which means maybe you got to update the whole stack at once, which can be annoying. Let's tie virtual chassis and stackable switches, back to the MLAG conversation. Yeah. So you are basically doing MLAG in a virtual chassis or in a stackable, effectively. But it doesn't, you don't have to do any fancy configuration like make a peer group and make a peer link and all that kind of stuff. You just set it up. It's a thing. You just use LACP, and it just so happens that you're coming from, there's always going to be rules about link aggregation groups. You got to have the same port types and so on, but you can spread those out across physical links in a virtual chassis or on a stackable, and it should just work. It should be fine. There were caveats back in the day when stackables were like a new technology and virtual chassis was new, where there was like asterisks and make sure and look out for and so on. But I think that's come a long way now, where that's not such a big deal. It's LACP, and you fire it up, and you, for redundancy purposes and common sense, you spread that out across whatever switches you want to spread it out across, and off you go. You stand up your bundle. Is it MLAG at that point? I mean, kinda. It's still multi-chassis, but I mean, it's happening in a different control plane context. Now, virtual chassis, whatever the vendor's virtual chassis technology is handling that for you, as opposed to it being this dedicated MLAG special thing, or like a Nexus, it would have been virtual port channel thing that you configured. Now you've got one gigantic switch that just so happens to be spread out across a bunch of physical switches. That's all. Stackable, the same thing. It looks like one gigantic switch that just happens to be interconnected with a bunch of stacking cables. So fire up your LACP, do your configuration, and it's spread across physical switches, and that's fine. Off you go. So it feels like on a virtual chassis or a stack that you're configuring your lag on one switch. because that's how it's meant to feel, as opposed to MLAG where it's, the two different switches and it's more of a tightrope act.
All right. I think that clarifies some of the things Kieren was asking. So lag, MLAG, and stacking. So I hope that we have explained the differences adequately. And I know I feel less confused. So I hope our listeners do as well.
Our podcasts are getting longer, Holly, but I guess we got some people told us that longer is okay. So if you don't mind longer once in a while out there listening, well, okay. You just got longer. This one's almost an hour.
Just you can pick what length is suitable to you. But yeah, I think, that wraps up our episode of N is for Networking today. I hope that this episode on lag, MLAG, MCLAG, put a slash there, help clear up some of the confusion around these similar sounding terms. And a big thank you to Kieren for submitting such a fantastic question. Your curiosity sparked a discussion that hopefully was valuable to both newcomers and seasoned pros alike. If you're curious about anything we've covered today or you have follow-up questions, don't hesitate to reach out, join the conversation in our Slack channel, or drop us a message at packetpushers.net/follow-up. We love hearing your ideas and questions, and we can make more episodes to answer them. Thanks for tuning in to N is for Networking. Until next time, this is Holly Metlitsky and Ethan Banks. Find us on the Packet Pushers community Slack or on LinkedIn. And just remember, networking isn't hard. Other people figured it out, so you can too.